and this is a video to extend some of the chemistry you know and add some more information to what you've already learned so that you are better prepared for an AP chemistry course. So we're starting here at the periodic table because I'd like you to have just recall some of the pieces that we know from the periodic table and also to relate it to the mole. So we have some whole numbers, and these whole numbers on the periodic table represent protons. So we have 3 protons, and those are in the nucleus. And then we have a mass number that represents how many protons and neutrons we have. And so now my mass is 7. Well, this is close to 7 and not exact. And if you recall, we have 2 different isotopes. So we have a lithium 7, I should probably put it there, which represents 92%, and that's why it's so close to 7. But there's also a lithium 6 with only 3 neutrons, and that represents 8%. So my mass is a little less than 7 for this. And it turns out that most elements have more than one isotope, and even though some are very, very small. Also, there's a mass energy thing, so not all of the mass is getting used, and so a lot of times the protons and neutrons don't have exactly one as the number. So that's what that number means, but for us, more importantly, it means the number of grams in each mole. And so there are 9 grams per mole of beryllium. And each of these numbers represents how many grams there are in a mole. There's this number called Avogadro's number that we'll be using later, maybe, which is how many different particles are part of a mole. So a mole is a collection or a group of substances or particles, and if there are this 600 billion trillion particles inside that collective sample, then you have 1 mole. And so each different type of substance can have 1 mole but have different number of grams because they have different numbers of protons and neutrons. So zinc, if you made a pile of 1 mole, it would weigh 65.4 grams because of the different numbers of protons and neutrons, versus carbon, which has about 1/5 the number of protons and neutrons, would only weigh 12 grams. But each of these pictures shows 1 mole, or 6.02 times 10 to the 23rd particles, in this case atoms, that are part of the substance. So they're all the same. So possibly a AP multiple choice would be, do you have a larger number of molecules? Do you have a greater mass? So it turns out that 1 mole, which would be some pile of hydrogen molecule and another pile of oxygen, and those piles would look just like this if these molecules were not gases. And then finally we'd have a pile of fluorine. And then each of these piles is a mole, and so what we know about the number of pieces or the number of particles is that they are the same, because the mole is a count of the number of things, and if they all have 1 mole, then we counted the same number of things. But their masses are different because the masses are based on their periodic value. So for oxygen, the average atomic mass is 1.01, so 2 of these would be 2.02 grams. Oxygen is 16, so that would be 32 grams. And fluorine is 19 grams per mole, and so this would be 38 grams. And so my largest value, largest mass would be the mole of fluorine. Okay, and then something a little harder that requires some stoichiometry. Well, I'm going to use stoichiometry, but you could think it out is, let's say I have 0.75 moles of ethanol, which has this molecular formula, and 0.60 moles of formic acid, and 1 mole of water. Okay, so I have all these moles, and I am just being asked which one has the greatest mass of oxygen. Well, if I counted all of the atoms, this would have the greatest mass of any of them, but they're actually only asking for oxygen. So what I need to do is I need to pull oxygen out of this molecular formula. So in one molecular formula of C2H5OH, I have 1 oxygen. So the moles of the molecule is the same as the moles of the oxygen. And for, let's switch colors so it's a little clearer. So here, when I have 1 H2O2H, formic acid, I'll have 2 oxygens. So now I'll have 1.2 moles of oxygen. And finally, there's only 1 oxygen, so it's 1 to 1. So we'd have 1 mole of oxygen for water. They actually asked for the mass, but it wouldn't matter. We're going to multiply each of them by 16 to get the mass. So that doesn't change the relative value. So this mathematics is our explanation, and we say formic acid. We should use a complete sentence, so we want to say 0.60 moles of formic acid has the greatest mass based on my calculations. Okay, so far nothing too difficult, nothing that you really needed to push yourself with, but didn't erase everything, did I? Let's get rid of this. Oops. And then, okay, practice, which is what I did. Okay. Percent composition is a regular chemistry topic we didn't get to this year. And in fact, all of these topics, if you were in a faster moving class, would have covered, or maybe a class that dealt more with concepts than with doing lots of labs and things like we did. So percent shows up a lot in chemistry, and there's a percent yield and a percent water in a hydrate. There's a percent error in this one, percent composition, but the idea of percent is always the same. So if I'm asking you for the percent composition, I'm really asking you for the percent of each component and how what percent it makes up in the substance. So in this little example, we're going to look at red marbles. So I have 1, 2, 3, 4, 5 red marbles. And so if I was asking for the percent of red marbles, there would be 6. And then I have to add up all of them together, 3, 6, 9, 12, 15, 16. So there's 16. So on the bottom you put total. So this is what I'm asked about, red marbles. This is what I'm going to give. And then you do that calculation and you divide by 100. Why did I put 6? There's only 5. So 5 divided by 16 times 100 equals 31.25%. 8%. Okay, so that's a basic percentage, but this is how it works in chemistry. So the first problem is not one that you're likely to find in a chemistry, in AP chemistry, but you could use it to learn. So how much hydrogen, how much carbon. So what does percent composition mean? It means that if I have 2.5 grams of hydrogen and 7.5 grams of carbon, what are the percentages that this makes it up? So what we need is this total amount. So when we add these two together, we get 10. So we're going to divide this by 10. I'm going to divide this by 10. And I get 0.25, 0.75. And then we multiply it by 100 to change my decimal number into 8%. So in this first problem, we're just learning when you're asked for percent composition, what are you supposed to be finding? Well, you're supposed to be finding the percent of hydrogen and the percent of carbon. Other compounds like nitrogen and oxygen or phosphorus will show up in these problems as well. And so you would just need to find the percent. Okay, this is a more traditional problem. So we have carbon, and we have hydrogen, and we have nitrogen. We have 7.34 grams, we have 1.85 grams, and we have an unknown number of nitrogen compounds. There's several ways to do this, so let's just keep going with the carbon. We know that there's 12.04 grams of total, so that will end up leading me to, 0.6096. I should only have 3 digits because I had 3 digits in my beginning, so 0.610 and then times 100 is equal to 61.0% carbon. I do the same thing with hydrogen, 1.01. I get 0.1536, and that's 15.36%, 123, or 15.4% hydrogen. Okay, so the two ways of finding the nitrogen. So the nitrogen wasn't given. There's no numbers for it. One way is that I know the whole thing adds up to 100. When you do these percentages, they add up to 100. Sometimes they add up to 101. Sometimes they add up to 99, but they're always close to 100. They are made-up problems by people. The other way to do it is I know that the whole thing adds up to 1204. So my suggestion, even though it's easier just to throw the number in here by doing subtraction, we have 60 and 15 is 76, so 34, is to figure out the nitrogen, which is 2.85, and solve that problem in the same way we have been solving it. Oops, not 2 decimal points. And then getting 23.7%. Okay, so when we do that, we are able to check our answer. We end up with 100.1%, and then we know we didn't do an error. So by doing all the calculations, we can decide whether we have an error or not in our problems. Okay, and then finally, let's do the last type of problem, which is actually pretty hard. So one is we're going to do empirical formula, and empirical formula is sometimes called the simplest formula. Because what that represents is it represents the lowest ratio of the elements. So when I did these percentages back here, I didn't know how much I had. I could have had even a larger sample of the same liquid would have given the same percentages. So percentages balance everything out, and you don't know how many, for in your case, how many grades did you get to get that percentage? It doesn't matter. It all averaged out. So the empirical formula of this glucose molecule is the simplest values that you get. So to simplify this, I could simplify it down to C1H2O1. And that would be the simplest formula. And if you were doing percentages, it turns out that this is the value you would get. You would end up with an empirical formula when you use the percentages to try and determine the molecular formula. So if you got this in your analysis, it could be glucose, it could be formaldehyde, and it could be acetic acid. So we have a poison, an energy source, and then a preservative, acetic acid, right, which is the component in vinegar. So all different, all have different properties, but they all would have exactly the same analysis. So first let's do some empirical formula finding. So what is the empirical formula? And then later we'll figure out how to tell the difference between these different molecular formulas. So we're going to start with the same process, create a table of the known information, which is what we did before. But this time we don't want to go to percentages. We want to solve this problem. How many ions and oxygens are inside the chemical formula? And when we do this is why we talked about the mole tells us the ratio here. So for every mole of iron, how many moles of oxygen do we have? So that's what we're going to solve for. So we're going to divide by the molar mass of iron, and that will lead to the moles that we have, 0.6261 moles of iron, and dividing by 16 grams per mole gives us 0.9393. Okay, well, we don't use these decimal numbers when we do any kind of chemical formula. So there's no chemical formula here or here or here that represents the kind of values I want to get. So I need to change these to whole numbers. Now the easiest way is to divide by itself. If I divide this by itself, I get 1. If I divide this by itself by 1. You want to do the same division to keep the ratio balanced or remain the same ratio that you're getting. So you have to choose which one to divide by, and we end up dividing by the smallest value. So 0.6261 is 1, and 0.6261 is 1.5. So the reason we do that is we have them both close to a whole number. And it turns out you don't round at this point. How do you get 1.5 to become a whole number? You multiply by 2, and then it becomes 3. And how do you get 1.33 to be a whole number? You multiply by 3. And how do you get 1.25 to be a whole number? You multiply by 4. These are the typical ones. Sometimes you get 1.66, and you still multiply by 3, which gives 5, 2, and 3. Yeah. So those are important numbers to recognize and have good math sense about. But this is what we're going to do. We're going to multiply this by 2 and multiply this by 2. So every operation after the initial determination of moles is exactly the same, so we keep the ratio the same. And now we have the ratio of iron to oxygen. So this is my empirical formula. Okay. Let's do this one. A sample analysis of nitrogen and oxygen, and 0.130, 0.370, divide by 14.01, divide by 16.00. Okay, so I didn't talk through very much, but I'm going to start with grams, and I'm going to change my grams into moles for this problem as well. And you can see that even though the numbers are decimal or very small, we go through the same process each time. So now I have my mole ratio, and I don't want this ratio to change, so everything I do to one I have to do to the other. I pick the smallest value and divide it into itself, which is not a mathematical calculation. You just write 1, and then you repeat that, and this time I don't have it again. Hey Siri, what's 0.02312 divided by 0.009279?
The answer is about 2.4916.
So I get 2.49, which is close to 2.5. So we'll multiply both of these by 2 as well. So not many surprises on this one. And we get nitrogen equals 2 and oxygen equals 5. So my empirical formula is N2O5. Nice. Okay, so there's a worksheet accompanying this video, and you will do that. All right, so last one, we're going to look at molecular formula. What is the molecular formula? And it turns out you can't do molecular formula without the empirical formula. So let's quickly do the empirical formula, where we have carbon and hydrogen and nitrogen, and 74.02 and 8.71 and 17.27. Now those are all percentages, but let's assume we had 100 grams, or you could have put decimals and say we had 1 gram. So let's say we have 100 grams of this substance, and that's how we got these numbers. So we're assuming we have 100 grams, and then we go through the same process. I'm going to go a little faster, assuming that you got it, and I'll just write out the values. So I end up with 6.163, and I ended up with 8.624, and I ended up with 1.233. The smallest value is 1.233. So I'll do that for all of them. And I end up with 6.996, which is 7, and 1. Okay. So I am ending up with 5 carbons, 1 hydrogen, 7 hydrogens, and 1 nitrogen. So that is my empirical formula. So the molecular formula is some combination of that. So it could be twice as big, or it could be 3 times, 4 times, 5 times, 6 times as big. It could be any number. The larger they are, the fewer iterations that probably are possible, but you have that. So what we need to do is we need to compare the empirical formula's molar mass with molar mass of each of these. And there's multiple ways to do this. You just find the molar mass of each of these. So here's 5 carbons, which is 60, plus 7, 67, plus 14 gives 81. And if I was to actually plug in the right values, I would end up with 8113. So that's how many grams there are in 1 mole. And my real molecule, go back to blue, was over here it said there's 40.57 grams in 0.25 moles. So that turns out to be, hey Siri, what is 40.57 divided by 0.25?
It's 162.28.
Grams per mole. Okay, so in this simple problem, you can see that it's essentially twice as big. So it's our answer is going to be this one, that it has this empirical formula that we calculated, and it has this molar mass. If it was a little more complicated, you would take the real mass, divide it by the empirical formula and get 2, and then you would take your empirical formula and you'd go, oh, I need to multiply this by 2. So that's how you change from empirical formula to molecular formula, is you do a calculation of empirical formula using this same process we've done over and over again to get an empirical formula. The empirical formula has a molar mass that could be doubled, 162, or it could be tripled, 243, and on, so on and so forth. Couldn't help myself. And then you just find what the molar mass is and compare it, and then you go, oh, this is what it is. So that's some of the more mathematical calculations that we had sort of skipped inside of our general chemistry class. I'm going to give you some worksheets with these problems on it and a reference for where you might find out how to solve these problems. And this should prepare you well for the beginning parts of AP Chemistry. So thank you for trying this out, and I appreciate your time and patience. Bye.